energy is already being used across the world. Billions of dollars have been invested in the technology and the world's first wave farm, opened near Porto, Portugal in 2008. At the European Marine Energy Centre in Orkney, Scotland, the world's biggest wave farm was approved for construction earlier this year. The 40-meter wave off the northwest coast of Lewis promises to deliver enough energy to power nearly 30,000 homes. Wave farms deploy massive buoys to turn the motion of waves into power. Optima Marine Power, the company running the project in Orkney, says that the huge yellow buoys have a maximum generating capacity of 800 kilowatts. The bright yellow machines measure 26 meters across and are installed at a depth of around 13 meters and around 500 meters from the shore. The waves pass through the Oyster Wave Energy Converter to turn the turbine that sends power to the reverse osmosis plant that then sends it out to different homes and that need the power. You can see as the waves pass through this wave farm. Polamis wave power generators. Each Polamis has 3 power conversion models that stick together to generate 750 kilowatts. Waves move across the sea and cause the Polamis to rise and fall in a snake-like motion, causing the turbine to turn and sending power to homes. In this picture, you see a Polamis wave power producer.
Natural well with pocket particle accelerators.
Researchers working in a laboratory in Dursbury, UK, believe that a pin-sized particle accelerator, like the large Hadron Collider in Switzerland, but much smaller, could offer a genuine alternative to fossil fuels. Powered by thorium, a natural occurring radioactive substance, a small-scale collider could generate significant amounts of energy. The Mail on Sunday estimates that just 1 ton of thorium could produce as much energy as 200 tons of uranium or 3.5 million tons of coal. The idea of thorium reactors is one that is under a lot of discussion these days. Clearly the physics will work, says Mankins, but he notes that there are always hazards in using natural nuclear material, even though it certainly will be safer than past nuclear reactors approaches. It seems likely to me that governors are not going to want a lot of radioactive material on their highways.
The pocket particle accelerators work the same way as normal nuclear reactors do, except for they use thorium instead of beryllium. The thorium goes through fission, creating energy, which causes the water to heat up and boil, making steam. The steam causes the turbines to spin, creating energy.
Thank you, Abel. Now to Francesca with hydroelectric power.
The theory for hydroelectric power is to build a dam on a large river that has a large drop in elevation. The dam stores lots of water behind it in the reservoir. Near the bottom of the dam wall, there is the water intake. Gravity causes it to fall through the penstock inside the dam. At the end of the penstock, there is a turbine propeller, which is turned by the moving water. The shaft from the turbine goes up into the generator, which produces the power. Power lines are connected to the generator that carry electricity to your home and mine. The water continues past the propeller, through the tail race, into the river, past the dam. Dams are the best way to harvest hydroelectric power.
Thank you, Francesca, and now to Shayna with nuclear power.
The nuclear power plant stands on the border between humanity's greatest hopes and its deepest fears for the future. On one hand, atomic energy offers a clean alternative that frees us from the shackles of fossil fuel dependence. On the other hand, it summons images of disaster. Quake-ruptured Japanese power plants belching radioactive steam, the dead zone surrounding Chernobyl's concrete sarcophagus. But what happens inside a nuclear power plant to bring such marvel and misery into being? Imagine following a volt of electricity back through the wall socket, all the way through miles of power lines to the nuclear reactor that generated it. You'd encounter the generator that produced the spark and the turbine that turns it. Next, you'd find the jet of steam that turns the turbine, and finally the radioactive uranium bundle that heats water into steam. Welcome to the nuclear reactor core. The water in the reactor serves as a coolant for the radioactive material, preventing it from overheating and melting down. In March 2011, viewers all around the world became well acquainted with this reality as Japanese citizens fled by the tens of thousands from the area surrounding the Fukushima Daiichi nuclear facility after the most powerful earthquake on record and the ensuing tsunami inflicting serious damage on the plant and several of its reactor units. Among other events, water drained from the reactor core, which in turn made it impossible to control core temperatures. This resulted in overheating and a partial nuclear meltdown. As of March 1st, 2011, there were 443 operating nuclear power reactors spread across the planet in 47 different countries. In 2009 alone, atomic energy accounted for 14% of the world's electrical production. Break that down into individual countries, the percentages skyrocket as high as 76.2% for Lithuania and 75.2% for France. In the United States, 104 nuclear power plants supplied 20% of the electricity overall, with some states benefiting more than others.
Nuclear power can be very dangerous, but it is still very effective because it does not use our fossil fuels.
Now we're going to explain why the new energy resources are better than the old ones. Okay, so first off, wave energy is more effective than the old hydroelectric power because waves are constantly moving, whereas the usual hydroelectric power is not always constant. The tides sometimes are in, sometimes are out, so you're not going to get the same amount of energy as you do with wave energy. And it's better to use thorium instead of beryllium in nuclear energy because 1 ton of thorium can produce as much energy as 200 tons of uranium. So that's way more effective, and you have to do less mining and use less natural resources.
This is a picture of what thorium looks like.
Thanksgiving! Have a great day!
Pictures.
No, I'm not ready.